Hello, I'm Morgan Allison, Application Engineer for Tektronix. Today I'm going to talk about real-time spectrum analysis. I'll be demonstrating using SignalVu-PC paired with the RSA507A. Real-time spectrum analysis is the practice of using specialized algorithms implemented in either hardware or software to significantly increase the number of spectrums processed per second. The main specification associated with real-time spectrum analysis is minimum signal duration for 100% probability of intercept. Thankfully, this is often abbreviated as POI. The POI specifies the shortest signal that can be reliably captured and displayed. Real-time spectrum analyzers capture signals that conventional spectrum analyzers or even vector signal analyzers would completely miss. A modern spectrum analyzer can capture between 20 and 50 spectrums per second under normal conditions, and this significantly limits its free-running detection capabilities. A real-time spectrum analyzer can capture millions of spectrums per second, giving you a much more reliable view of what signals are present in the span of interest, and detecting very low duty cycle signals, or even signals hiding underneath other signals. Tektronix calls their real-time technology DPX, and it sees a lot of use in spectrum monitoring, signal detection, and interference mitigation applications, allowing those users to characterize environments and pinpoint signals of interest much more quickly than before. At its core, the DPX display is still a spectrum display, so the controls are all but identical to those of spectrum analysis. Center frequency, reference level, span, and RBW do the same things in the DPX and the spectrum displays. Because we're capturing significantly more spectrums per second than a normal spectrum display, we need to present the data in a useful way. We stack up all the spectrums we captured on top of each other and assign a color to each screen pixel based on how many times a spectrum trace point landed there during our acquisition. This means that red signals occur most often, blue signals occur the least often, and yellow and green signals are somewhere in between. This colorization information is useful because it provides some time domain information in a primarily frequency-oriented display. Let's give an example of how real-time spectrum analysis is better at detecting signals than normal spectrum analysis. I have a wireless router in the room with me, and I've connected an antenna to my RSA. I'll start from a preset, and then I'll set my center frequency to the first wireless LAN channel in the ISM band, which is at 2.412 GHz. The signals coming from my wireless router are lower in amplitude, so I'm going to adjust my reference level to a suitable value that maximizes dynamic range without overdriving my front end. Now you may notice that there are signals popping up occasionally on the spectrum display, so we know there's something out there. Let's get a better look by bringing up the DPX display. You can immediately see the difference between the spectrum and DPX displays. The DPX display is capturing much more activity than the spectrum display. There is a Bluetooth device in discovery mode in the room with me, and I can see this immediately in DPX, but it's not so obvious in the spectrum display. This signal was definitely not planted for the purposes of this demonstration. Another useful DPX feature is the DPX spectrogram, which uses the DPX spectrum data to create a waterfall plot that shows the spectrum over time. The horizontal axis is frequency, but now the vertical axis is time, and the colors denote amplitude rather than frequency of occurrence. The DPXogram is a very useful way to keep track of spectrum activity over time. If I switch to split in the drop-down menu here, I can stop the acquisition, pick the trace I want to see, put a marker on the waterfall display, and move it around to see what was occurring in the spectrum at that given point in time. Much like the normal spectrum display, the DPX spectrum display can also sweep across spans larger than 40 MHz. Simply change the span in the DPX display and SignalVu-PC will take care of the rest. Swept DPX is very useful for quickly determining what the environment looks like over a large frequency range. note that the DPX spectrogram cannot be used over larger spans. There is a common misconception that real-time spectrum analysis is complicated and narrowly focused. In reality, using the real-time capabilities of Tektronix instruments is almost identical to using them for legacy spectrum analysis, while providing significantly more information to the user. An added benefit is that you can have the DPX display running while performing other measurements to make sure your signal environment isn't changing without your knowledge. You can save a file that includes the contents of the DPXogram, providing you with a large amount of spectrum data in a fairly small package. You can save up to 60,000 spectrum lines with full control over the amount of data used to create a single line on the waterfall. There's a handy readout that displays your saving capacity in terms of time. Higher performance Tektronix RSAs go a step further, allowing you to trigger using the data in the DPX display. So now, in addition to seeing intermittent signals, you can also capture them directly and then perform further in-depth analysis on those signals of interest. This video gave a basic overview of real-time spectrum analysis using the DPX display and demonstrated the waterfall plot of the DPXogram. Thanks for watching.